The simple Atwood machine is a modified version of the traditional Atwood machine created in 1784 by English physicist and mathematician George Atwood. The original Atwood machine is commonly studied in classical mechanics courses, and its motion is completely understood both in Newtonian and Lagrangian formalisms. On the other hand, the swinging Atwood machine is a far more complex system due to the addition of another dimension of motion for one of the masses. In an ideal system without dissipative forces and massless pivots, the behavior of the swinging Atwood machine can be analyzed using the Lagrangian formalisms with generalized coordinates r and theta. With the Lagrangian written out in terms of kinetic and potential energies, Euler-Lagrangian equations can be solved in order to find the equations of motion for each of the generalized coordinates. The solution to the first Euler-Lagrangian equation is as follows. And the second Euler-Lagrangian equation with respect to generalized coordinate theta is if we define the quantity mu as the mass ratio between the two weights, then the equation of motion for the swinging Atwood machine can be expressed as However, these equations do not have analytical solutions that can be easily solved for. As a result, one of the most interesting features of the swinging Atwood machine is that it is an example of nonlinear dynamics. By looking at the equations, we can see that they are both nonlinear differential equations, hence why they don't have any analytical solutions. Without these analytical solutions, it is difficult to predict behavior of the swinging Atwood machine because it varies greatly depending on the initial conditions of the system. Chaos systems are of interest in a variety of fields outside of just classical mechanics. Many real-world phenomena, ranging from weather to stock markets, can be modeled using nonlinear dynamics. Additionally, a lot of research is currently being done to look how chaos systems can be utilized for encryption and cybersecurity due to their seemingly random behavior as potential applications for random number generation. Because of this variety of applications, it is of interest that alternative models for understanding the behavior of such systems like the swinging Atwood machine be developed so that they can be understood regardless of the presence of analytical solutions. Therefore, in order to model this system, both experimental and numerical techniques were used in order to gain a better understanding of how chaos results from various initial conditions for the swinging Atwood machine. We first have our runaway solution, which shows that with friction there is only one solution. The smaller mass works to save the larger mass. In the next solutions, we have a system with very little friction, as we used pulleys lubricated with oil. The mass ratio 1.16 orbit shows a smile orbit, oscillating between two extremes. The mass ratio 1.2 orbit shows an upward smile that, in total frictionless environment, will move up and down at extremes as well as left and right extremes. The numerical analysis for this project was performed using the Runge-Kutta fourth order technique, which makes it possible to solve first order linear differential equations. In order to get the equations of motion into a format that could be analyzed numerically, these substitutions had to be made. Once the differential equations were altered into this format, the ODE45 function on MATLAB was used to perform the numerical simulations. Simulations were run for two sets of initial conditions that could be then used in comparison to the experimental simulations performed. These initial conditions were an r of 2 and an initial angle of pi over 2, and two different mass ratios of 1.16 and 1.12. When we compare these results to the behavioral patterns of the experimental simulations, we can see similar changes in r and theta for both analyses. These results provide a complete behavioral description of the evidence of the chaotic behavior in the swinging Atwood machine, without the presence of dissipative forces. To wrap everything up, by using experimental and numerical models to show the behavior of the swinging Atwood machine, helps us understand more complicated subjects not only in physics but in chaos theory as a whole.